AX7, miscellaneous forces. There are various forces. In practice, the friction is a very important force. To consider friction, we always have to understand what the normal force is. A normal force on an object is normal to the surface, and it does not carry any tangent component. This tangent, normal. Normal is perpendicular to the plane, and tangent is tangent to the plane. So normal force is not a fundamental force. It is just the projection of a force that is normal to the surface. It is a contact force. Sure, it exists only if it touches. An object touches the surface, so it is contact force. Normal force never exceeds the applied force in magnitude. Sure, it just cancels the pressure pressing down on the surface. If the normal force is greater than the applied force, this strange thing happens. Suddenly an object springs up without any applied force. That is impossible. So normal force does not have the component tangent to the surface, right? It is not a fundamental force. By the fourth statement, direction of friction is always tangent to the surface. Friction is opposite to the velocity of an object that is sliding on a surface. So it is opposite to the velocity, and velocity is always tangent to the surface as long as it touches the surface. Static friction is always greater than the kinetic frictional force. Not always true. The static frictional force varies. It depends on the applied force, and maximum value of the static frictional force is greater than the kinetic frictional force. However, if I apply a very tiny amount of applied force, the static frictional force is just make it in equilibrium, so it can be very small. But the maximum, as far as the maximum value of the static frictional force is concerned, it is greater than the kinetic frictional force that is constant. Friction does not have components perpendicular to the surface. Sure, friction can be a single external force applied to an object. That's possible. The direction of the tension on a string is always tangent to the string. Or for example, we consider suspension bridge. There's a bridge. At tension, usually we do not consider the weight of this the string or wire. However, if we consider that, it becomes an exponential function. Exponential function that is composed of a cosine hyperbolic or sine hyperbolic. The general solution of the suspension bridge is this kind of function. However, if we do not consider that kind of complicated situation and whatever, any part, any line segment of this wire carries the tension. On the left side is downward, on the right side is the upward, something like that. So it is tangent to the curve, tangent to the curve. 조원이가 질문한 거야? 질문할 거야? Okay. Only a tensile force applies to the tension. Tensile. Tensile is an adjective of tension. So tensile force. Compressive force. Compressive force is a pressing. So there's a wire or string. There is a no compressive force. If we compress the string, then it does not transmit any force. Without friction, one cannot open the door by turning the doorknob. This is doorknob. This is door. Without friction, you cannot rotate this. It is based on the friction. You cannot write with a pencil. Sure, you cannot grab your pencil without friction. You cannot walk, so you cannot walk because there is no friction. You cannot keep the ground, and you cannot go forward. A rocket cannot accelerate. Oh, it is nothing to do with friction. It is Newton's third law, action and reaction. It ejects the gas and the rocket goes forward. So it's action and reaction. 5, we have two objects that there is no friction, and distance from the wall is x, and distance from this shelf is y, and this string is unstretchable. That means it is not elastic. It does not carry any spring in it, and there is no mass. But the mass, it is impossible to have zero mass, but the mass of the pulley is negligible, as well as the mass of the string is negligible. And we consider the tension T in here. Tension applies to this T and T prime in here. If we ignore the mass m equals 0 for this pulley, then magnitude of tension must be preserved. Magnitude of the tension must be preserved. The role of a pulley is to transform the direction, change the direction of the force. That's quite important. As far as this mass of the pulley is 0, then the magnitude of the two tensions are the same. And then we can write down the equation of motion for capital M. It has an acceleration, and its net force is tension only. Sure, there is a mass, there's a weight, but that is exactly canceled by the normal force of the shell. And then why don't we consider the magnitude of A only? But in here, the force is along the horizontal direction, and this, as far as the yellow block is concerned, is acceleration is downward. But if we consider the magnitude only, including the sign, then it's fine to write down the equation of motion for the yellow block, MA. But it is applied by the two forces. One is gravitational force, and the other is tension. So we have T prime. A second. Mg minus T prime. But as I told you, if I ignore the mass of the pulley, then T prime and T, they have the same magnitude. So let me just erase prime. So if I sum these two, M plus M, A equals mg. So acceleration of the whole object is mg over m plus m, something like that. So there's a mistake in it, so we have to consider this. Next one, We frequently use the exponential function or logarithmic function for solving the equation of motion. It is a very important, very, very important. And you know, everybody knows this. And the log 1 is the 0. ln means natural log, whose base is e, right? 7. A box of mass m is moving under uniform friction from the origin with the initial velocity. This is the initial velocity at t equals 0, and at t equals capital T, it makes a complete stop. So what is delta V? Delta V is a final minus initial. So minus V is the delta V during this time interval. Acceleration, that's wrong. It's a minus V over T is the acceleration. Velocity must be of the form, yes, if I substitute T equals 0, it is a V, right? If I substitute T equals capital T, this vector becomes a 0. So this is a exact formula for the velocity. And if I integrate this one more time, you'll find this. You can factorize this over a factor as a T, and the V is also factored out. You remember x equals this one this is constant acceleration motion. This is a, this is minus v over t acceleration, and the initial velocity is capital V, and the initial position was 0. So if I sum them all, this is the result, right? Position at time t. Why don't you just substitute t equals 3t? You'll find the answer. Coefficient of kinetic friction, you'll find it is ma equals mg times the kinetic frictional coefficient. Then mass cancels, so mu k equals a over g. You find the magnitude of the acceleration, that is a magnitude of v over t, and you divide it by the gravitational acceleration g. Number A. We have a damping force. Because of the air friction, one cannot arbitrarily accelerate. This one shows the simple modeling of the damping force as a linear function of v, but in fact, in practice, the velocity, if the velocity increases, this power dependence appears, and for example, if you launch a rocket, you will experience a very high power in V. But in our case, let us just consider a simplistic case, and this is an approximation as a linear. The damping force is linearly proportional to the velocity in opposite direction, because b is a positive, minus b is a negative, and minus bv, velocity, is opposite to the motion. Velocity is along this direction, and damping force is opposite. So if we write down the equation of motion, what we find is F equals ma, m acceleration equals minus bx dot, but we consider the gravitational acceleration applied to that object. So this is the equation of motion. We simplify this into a one-dimensional case, so just to let it fall down along the straight line perpendicular to the ground. So it's parallel to the gravitational acceleration. In that case, we just scale this mass out, then the resultant equation of motion is this. Usually students, they want to learn differential equation first, but as I already told you, differential equation that is just originated from the equation of motion in physics. So we don't have to learn mathematics very much. This looks like a second order linear differential equation. Sure, you can apply that method. However, this one can be solved by a high school student because it is integrable exactly. Let me substitute x dot, substitute v for x dot. Then it is a acceleration is a time derivative, and this is a b over m velocity equals g. Why don't we move this one to the right hand side? Then we have dv equals minus b over m v plus g and dt. And now there are variables v and t, but I can divide this factor both sides. Then what you find is a 1 dv over minus b over mv plus g, and right hand side is time. Now, high school student can integrate left side, that is a log, and right hand side, it is just a t. This is a trivial integral. So do not refer to differential equation. It is just the equation of simplest equation of motion that can be integrable with elementary way. So in here, this gamma is introduced, that is a b over m. So by making use of this, why don't we multiply this minus, we just multiply minus gamma to numerator and denominator, then we find the simplest form. So this is a log. This is total differential of log, right? And right hand side is just this one. And if you integrate from the initial state to some time, what you can get is subtract the final log v minus g over gamma subtracted by log v minus g over gamma. Here it is a 0, so it is a value at t. And log a minus log b is just the log a over b. So this is the result, and the right hand side is trivial integral. Now we have log a equals b style, and your answer is a equals e to the b. This log is just whose base is e, right? So that's the reason. So finally, what I obtain is a v of t minus g over gamma over v0 minus g over gamma equals e to the minus gamma t. And as we know, this initially it was at rest. Initially it was at rest. v0 equals 0. So v of t minus g over gamma equals, this one is gone, so minus g over gamma e to the minus gamma t. So move this term to the right hand side, you will find this is, now gamma is b over m, so substitute this value to here and simplify the result in this form. Okay. So because B is positive, mass is positive, and time is positive, exponential B over mt goes to 0 strictly as the t goes to infinity. So this term will disappear as time goes on, and you will find this one is just a constant value. This is called the terminal velocity. Okay. Next, we consider the case if it is possible to reproduce the original result without damping. If you first substitute b equals 0 directly, mathematicians or many students might think that, oh, it is not well defined function because I cannot substitute b equals 0. However, you will find this one has also proportional to b, and that cancel exactly in the limit as a b goes to 0. Let's see. We learned how to expand the Taylor series expansion of x where about x equals to 0. So I can expand this one. You will find this one and this one cancel exactly, and this one and this one. This is the leading contribution because this is x equals b over mt. So if I substitute this one, neglecting the higher order piece, this one is the leading contribution inside the bracket. You will find this bb cancels, and you exactly reproduce the v equals to gt, that is a constant acceleration due to the gravitational acceleration. Just now it is free to substitute b equals 0 in every term, so your solution has a correspondence with the free falling without friction. Next, we consider uniform circular motion. Not a uniform circular motion, it's a periodic motion. Goes faster, slower, faster, slow. We will learn after we study the energy conservation, but before that, it is still possible to look into various aspects of the circular motion. It becomes slower and faster, and motion is always tangent. And at these 2 points, as far as the 2 points is concerned, it is approximately a uniform circular motion temporarily. You will find in here, suppose that you know what the speed at point B is. In that case, you can make an approximation of a uniform circular motion that the net force is toward the center and the magnitude is mvb squared over r. As you know, this particle is constrained to follow the circular track, so it is possible to be applied by the normal force. However, in a very small velocity, barely passes through this top point B, in that case, you can ignore this. I mean, there is at least mg is applied downward. And it is possible to have a normal force either this direction or that direction, because there is a hole in it and drag is passing through this particle. In that case, it is possible to apply normal force along this direction or in this direction. Sure, if it is on top of this particle is over a track, normal force can be applied to this direction only. Or in this case, normal force can be applied to this direction only. But in this case, it is possible to apply normal force in either direction, up or down. So what you have to consider is there is mg, that is constant. And there is a normal force. Normal force, I don't know whether it is up or down. Mg vector plus the normal force should be the net force. And the net force must be mv squared over r, and it is directed to the center, minus r hat, so toward the center. Okay. At A and C, it is accelerating, and normal force does not apply the tangential force because we do not have a friction. So in these 2 points, the direction of the force is not toward the center. So that's the reason why I do not ask any question regarding point A and C. Instead, at B and D, they are approximately a uniform circular motion. So you can solve it in this way. Okay, there's something wrong with this figure. F has a component along the E1 direction. So this is E1. So I have to correct this one as E1 hat. So F is pressing down the block that is attached to the wall, and there is a force F. Because this block does not penetrate the wall, the normal force from the wall cancels this force exactly. So F plus N must be 0. Okay? And then because of this normal force, there is a static frictional force, and the maximum value, it is not wrong. It is not wrong. It is correct. So E2 is missing in here. E2 is downward, and frictional force is opposite to the direction of gravitational force. That is opposite to the gravitational force. Sure, if it is sliding up, then frictional force will be going down. But in here, it is in equilibrium, and the additional force that is the gravitational force tends to bring it down. So the frictional force is opposite to this gravitational force. So that's the reason why it is E2 is in here, E2 hat. So this is mg E2 hat, and frictional force is upward, but it varies. Its value varies depending on the situation. If the system is in equilibrium, then the static frictional force must cancel this gravitational force. If it is sliding down, the frictional force is going up, and because it is moving, it should be replaced with the kinetic frictional force, and in that case, we have to replace this one with the mu k instead of mu s. And mu s is used only when the maximum value is achieved. And this maximum value of the static frictional force is slightly greater than the kinetic frictional force that is constant in magnitude. So if it slides down, the net force along the horizontal direction cancels, and there is a gravitational force mg, and in case if it is moving, fk and fk vector should be minus mu k, and n is the exactly same as the magnitude of f, and e2 hat will be this value if it is moving. If it is moving, that it should be ma. Okay? If I substitute these values, then what I get is a g is parallel to e2 hat and minus mu k n over m. I have divided both sides with m, so if I divide it this way. And then what is n? N is the same as f dot e1 hat. E1 hat is this direction. So magnitude, this is a magnitude of f. Okay, that's fine. This one, we already solved this problem. The net force on this object is, net force. Net force is just if I know the velocity, then we take the time derivative to find the acceleration and multiply this one by mass, then I can obtain the net force. So this will be the answer. So, okay. So first what I have to do is take the time derivative, and because it is constant, acceleration is mg over b minus b over m exponential minus b over m t. This one disappears if I take the derivative. The answer is v over m e b over mt. That is acceleration. Multiplied mass, so F net equals ma equals b e to the minus b over mt. That is the net force. Oh, wait a second. I have, this one is missing. Let's see. Let's do it again. A equals mg over b multiplied by minus b over m e to the minus b over mt. So this one becomes a plus, cancels, bb cancels, so a equals a g e minus b over mt. So f net equals ma equals mg e to t minus b over mt. Right, this is correct. Initial velocity is 0. Initial velocity, if I substitute t equals 0, v0 equals mg over b 1 minus 1 equals 0. Right. Displacement during the time interval is, so correct answer is given here. Just what you want to do is just to evaluate the integral of this. Delta x equals 0 to t dt velocity. So if you make a definite integral from 0 to t, the answer is this. Dimensions of b. So we remember f equals minus bv, right? In that case, f equals mass, acceleration is length, time minus 2, and b is dimension, velocity is length, time, this way. So dimension of b is mlt minus 2 and lt minus 1. The answer is the L cancel and mt minus 1. That is right. A pug is making a uniform circular motion, So if it is making a uniform circular motion, there should be a net force toward the center, ER hat minus, and the magnitude is mv squared over r, or mr omega squared, because v equals r omega. Okay, in here, the force is tension only, tension. T is in here, and there is nothing in here and no friction. In that case, the magnitude of tension is always preserved. This tension and this tension magnitude must be the same, just like the case when the string is attached to a pulley that is massless. And we know it is stationary because the uniform circular motion, the radius is fixed, therefore it is hanging on a same height, the fixed height, and time derivative of this height is 0. We know this is in equilibrium. Tension is upward and mass produces the weight mg. The tension must be the same as mg. This tension must be the same as mg. So everything is done. So from in here, we don't need this tension anymore. So what we want to know what the speed is, just multiply the reciprocal of m over r and simplify the expression to find the square root of capital M Rg divided by small m. We have a binary star by two stars, and there is a center of mass. In the previous class, we learned the center of mass of the two-body system, and the center of mass of two-body system with M1 and M2 is what we learned from elementary school, internal division. Point of internal division with the ratio upside down, M2, M1. It is not M1. If it is M1, the ratio is M2. It is crushed because the center of mass of two-body system is M1, M2, M1, X1, M2, X2. So this is the formula of a center of mass. Okay, so in here, there is no external force except for the attractive gravitational force between the two celestial bodies. Gravitational force is the centripetal force for particle. This is a celestial body B, a celestial body star A, and star B. Okay. And what is the gravitational force? The formula gives the gravitational constant G and product of the two masses MB and MA and distance squared. The radius is a small r and this is a 2r and this is r. So the distance between the two stars is 3r. So I have divided by 3r squared. This is 9r squared. The magnitude of the gravitational force satisfies, okay, because both of them are making a uniform circular motion. If I look at this, then it is a gravitational force must be the centripetal force applied to this object. And centripetal force on this object moving on a circle with the radius 2r is mr m o m a r a omega squared. That is m a r a is 2r omega squared. And because of the action and reaction, the two forces are the same. The gravitational force applied to this star B should be the same as this, and that is mv rb omega squared. And what is rb? This r. So mv r omega squared. That's fine. The ratio of the two masses is ma and b. Because the radius, this track shows this is a radius r and this is a radius 2r, mass, this one is a heavier and this light one. And we know the internal division of mass 1 and mass 2, the distance is m2 to m1. Okay, so this is wrong. This one is a heavy, mb is a heavier by a factor of 2. Same problem, you just rewrite this one. And total kinetic energy of the binary star, total kinetic energy is 1/2 m. This is actually x dot cm equals 0. So you remember it is a 2 mu p squared. And what is a p? What is p? That is a mu r dot. Or simply you can compute ma 3a squared plus 1/2 mb 3b squared. And what is VA? VA is RA omega. What is VB? RB omega. What is RB? That is R. What is RA? That is 2R. Substitute and you'll find the answer. Sure, this is the reduced mass product of two masses divided by sum of the two masses. The two-body system has a special characteristic mass called reduced mass. Next, we consider Atwood machine. Atwood machine is a two massive objects connected by the string that carries a certain tension. And for simple case, this pulley, mass of the pulley is ignorable, and we do not consider the frictionless. In that case, it is something like the total system m plus m is applied by the two forces in one dimension. Mg is applied to the right and capital Mg is applied to the left. So net force is something like m minus mg, and that is applied to the sum of the two masses with the acceleration. So acceleration should be m minus m over m plus m, g, something like that. But let us solve this problem by making use of a systematic way of linear equations. First, we have the t and t prime, and t prime is the same as t as far as the mass is negligible. The mass of the pulley is negligible. Okay, is gravitational force is down, and there is we have tension, the same tension applied in here. As I already told you, the tension is applied to in either direction. In this case, it is going up if I look at this mass. But tension applies to the pulley is going down. Okay. So you should be careful with choosing the direction, even though the magnitude is constant. If you look at this one, tension is going down, and if you look at this one, tension is going up. Anyway, the equation, we have two equations of motion. Capital M is, let us consider this direction as to be positive direction. In that case, it is mg minus t. And in that case, this is ma. Going up is positive, so it is positive t minus small mg. Be careful with choosing the direction. In here, you will find the sum, tt cancels, m plus ma, and m minus mg, and you will find the answer. But you can construct a linear equation from here. You find out the a and t simultaneously. In that case, you just move these tangents to the left-hand side, construct a linear equation that is ma plus t equals mg, and small ma minus t equals minus mg. This is a product of m1, small m minus 1. You multiply a and t, and right-hand side is mg minus mg. Now you multiply the inverse matrix of this 2 by 2 matrix, inverse In here, to simplify the analysis, we multiply the minus sign in here, and it becomes a positive. Then, the inverse matrix can be obtained. AD minus BC, determinant, AD minus BC. Exchange this, 1 capital M, put negative sign on it, multiply A and T. So the answer is, no, not A and T. Right hand side, mg, mg. The left hand side is A and T. So if I compute this, m plus m, capital M minus small m, g, and the second one is, they are the same, m. Two times mm over m plus mg. Okay, so factor of 2 is missing in here. Okay, this number 16 is very similar to this problem. We have weight, this mg, and we have additional force applied to this object. Then this F has the two components, parallel to the horizontal and parallel to the normal. So all of the external forces are this external force, and this gravitational force and normal force. As far as the vertical component is concerned, they are in equilibrium. The only contribution that is not in equilibrium is a horizontal direction. So resultant acceleration must be parallel to the right direction. So because the vertical component must cancel, we have mg and f sine theta. F is in here. This is f sine theta. So n f sine theta, their sum must be the weight. So this is the same as this. Okay? This weight is sustained by the sum of the normal force and vertical component of F. Okay. So because of this, I can determine the magnitude of the normal force. Once the magnitude of the normal force is determined, I can compute the kinetic frictional force. Kinetic frictional force is the normal force multiplied by the kinetic frictional constant and multiplied by a unit vector that is opposite to the motion. That is a minus E1 in here. This is E1, E2. Okay, as a result, acceleration is the net force is the horizontal component of F, and in opposite direction, we have kinetic frictional force that is subtracted because we are considering acceleration. We divide by the mass of this object. This is the answer for the acceleration of this box. (17) Acceleration is always this is uniform circular motion. This is velocity. Acceleration is toward the center. And the velocity, this is a velocity. This is acceleration. It's always perpendicular. Velocity is always tangent to the circular path. Velocity is always tangent, right? The acceleration is always perpendicular to the path. Sure, acceleration is perpendicular to the path. Path is this one. Acceleration is perpendicular. Centripetal force of a constant magnitude is always directed toward the same fixed point. That is the center of the circle. The acceleration along the tangential direction may arise depending on the situation. No, not at all. It is possible only if there is a torque. For example, Atwood machine. For example, this pulley is making a uniform acceleration, so its tangential acceleration exists because of the torque. Torque is the, later we will study R cross F, the force applied to a rigid body that makes the turn faster and faster. That is a tangential acceleration. But in uniform circular motion, tangential acceleration does not exist. So 18, this is a little bit complicated, but in here we have a very simple case. They are in equilibrium. This is a wait second. Anyway, we have pulley of massless pulley. So this tension, this tension, this tension, this is massless pulley. This tension, tension, tension. They have the same magnitude. If you look at the whole system is sustained by these two forces. And the whole mass is m plus m. Okay. I have TTT, and this TT is sustained by this one. So this one should be 2T. I have a TTT, and this T is sustained by T. So there is a mismatch. This is 2T, and this is T. But as long as the tension of the string is concerned, everything is TT. This is the reason why this one is in equilibrium. I have TT, so TT is a sustaining capital M. Aha, 2T must be mg. And this T must be small mg. Aha, TT, they are the same. So T equals 1/2 mg equals mg. What's that? This is 1/2 capital M. If I use these two pulleys, I can sustain this heavy object. This is a heavy, factor of 2 heavy. I can sustain the heavier object with the smaller force. This is a very useful tool of moving pulley. So the solving the solution is straightforward, is given explicitly here. So people uses the crane, the repeating, the just repeated use of this moving pulley. You can sustain a very, very heavy object. Okay, that's it for today.